Start. Okay, hello everybody. Welcome to this language design session of PADL. Today, our first speaker will be Tiark Rompf, so take it away.
Okay. Introduction, thanks for coming. This is joint work with my student Supun, and we've been working on this little query language called Rhyme for some time, and I'm very happy to talk to you about this a little bit. Okay, so what are the goals, right? We want to do high-level data manipulation, and specifically manipulation and querying of nested data structures, right? So think about stuff like JSON or potentially tensors, or if you want to go fancy, XML or things like that, right? And of course, there's been a lot of prior work in that area, right? So if you remember, XML databases were a hot thing. Maybe a decade ago, things like XQuery, and today we have GraphQL and JQ, and of course, thing then as an end result in a kind of nested tree-like fashion, or produce a dashboard or something. It's not something that really just falls out of the database itself. Okay, so we need to do additional work on top of that. So that's kind of what we would like to do, right? Have one query language or query system where we can, put in some semi-structured data and essentially, get out something like a dashboard or another tree-like structure. So let's consider some very simple examples, right? So here I have a JSON data set. It's really just a flat list of tuples, mapping, cities to their respective country and the population. And of course, sort of the most basic constructs we can have for querying these things are eliminators and introduction forms, right? So I can do direct element access by, essentially providing a path, right? So, take the second element and then give me the country. So in that case, I would get back France. Or I can also create a new nested structure as a result, right? So maybe I want to wrap my query result in another object, okay? So I can build a new object with a key first and then say, okay, I want to get the 0th element and then the country. And then I get back something like a JSON object that maps first to Japan. So, pretty boring so far, right? So if we want to do anything interesting, we got to have some form of iteration, right? Iterate over things, do aggregation, and so on. And this is where things look a little different here in our language Rhyme than in traditional languages. So iteration is implicit. And we have this wildcard operator star, which we can use to express iteration, right? Traversing collections of various forms. And then we can, have operations that reify the result of this iteration, right? So if I put things in square brackets, basically that means I want to construct an array, and I'm not specifying the elements individually, but I, just provide a query expression here, right? So I say I want to traverse data with, any kind of key and get the cities, and what I'll get back is an array that contains the city names, right? So Tokyo, Beijing, Birmingham, and so on. I can also do aggregations, right? I can say, I want to build the sum of, all the populations of the cities here, can compute the maximum, right? So any other kind of reduction operator you can implement in this way. And again, we can put this into a nested data structure as a result, right? So I can say I want to build a record that has a field for the total and for the highest, right? And then I use the sum and the maximum query to compute the values for these two fields, okay? Another thing we can do here with this wildcard notation is if I use that on the left-hand side of an object constructor, so have the key be computed from a query, then that gives me group by semantics, okay? So here what I'm saying is I want to build a new object where the keys are the countries, and then for each country I want to compute the sum of the populations of the respective cities. Okay, so I get back an object like this, where the keys are, Japan, China, France, UK, and then the values are the sum of the populations of the cities from our initial data set. Okay, and you can think about if you wanted to express the same thing in a high-level language like JavaScript or Scala or whatever, right? Then, this is already slightly complicated, right? You have to think about how to traverse things, right? There's got to be some kind of index data structure, maybe. And the question is also, okay, how fast is it going to be? Okay, so I'm going to talk about this a little later, but we're able to generate pretty tight code from this, and fuse loops and so on. So, of course, if you know about declarative programming languages, you already might have this idea. Well, this star, right? That looks like a logic variable somehow, and in fact, it is. Right? So instead of just using a star, we can use any kind of identifier. We can say star A or star B, and actually use that as a logic variable to say, well, this is really the same iteration. Okay? And now if we use multiple of those, then like in Datalog or any other declarative query language, what we get is a join operator. Okay? So again, using a very general facility, we get a lot of power here. For example, here we're doing a self-join operation, and we say, okay, for every country, we want to compute the sum of the population of the cities in our data set. But we don't just want to have the sum, we want to have a relative sum, right? We want to have that as a percentage of the overall population. Okay? So we can express that like that using two iteration variables, and what we get back is our record, which has these populations as fractions of the total. And of course, we can put that together, right? So, the syntax is relatively flexible. So I can describe a, compound object that has, aggregation subtotals at multiple different levels, right? So I can say I want to compute the total at the top, and then I also want to include all the countries, and I want to compute a total per country. And then for each city, I want to compute a relative sum that takes the population as a percentage with respect to the overall one. Okay, so I get a structure like this, which has totals and subtotals in the right places, and then for each individual city, we have a percentage here. Okay, and again, sort of think about how to do this using either a SQL query or a general purpose programming language, and you can see that it's not obvious how to do that, right? And it would probably take longer than what we have on the slide here. The key thing here from a language design perspective is that an expression like we have here, right? So data.star_a.population, the meaning of that depends on the context, okay? If I just use that as a top level, it means, okay, sum everything. If I use that in a situation where I have the star A as a key, then that means it's actually grouped by that key, okay? So what these expressions mean is context dependent, and that gives us a lot of the power here. So how about other paradigms, right? We talked about JSON so far. Maybe we're interested in tensor computations, okay? And for tensor computations, one thing that's popular in ML frameworks, for example, is this Einstein sum notation, where basically, say we want to do a matrix transpose, we just specify an index space transformation, right? So index space ij should be transformed to index space ji. And we can express basically the same thing in rhyme using these logic variables, okay? We can say compute a new object with outer keys j and inner keys I, taken from our input data b indexed with first I and then j, okay? That's a matrix transpose. And in a similar style, we can do many other tensor operations, right? So already talked about transpose, then maybe we want to sum all the elements in a matrix. Maybe we want to sum by columns, sum by rows. Maybe we want to multiply two matrices. Maybe we want to multiply them any element-wise, right? Or we want to just restructure our data set in some way, right? So if you're doing something with images, you might want to change the order of color channels or do some pre-multiplied alpha or some of these kind of transformations, right? So all of these are expressed relatively easily. And if you say, well, okay, this rhyme syntax is slightly more complicated than the actual Einstein sum formula, then you can implement a little parser for Einstein summation that produces this rhyme code as its output. Okay, so we can add a front end and use that as an IR and have something fairly generic. The interesting part, of course, is now that we can express multiple paradigms here, we can put them together. Okay, so oftentimes when you want to, feed something into an ML model, you need to do some pre-transformation. So maybe you're taking some JSON data as your input and you want to do some data cleaning, transformation, put it in the right format, and then you want to do linear algebra on it. Okay, so here's a very simple example from a crime data set where again we have cities and populations, and then we have the number of robberies. Okay. So here what we want to do is essentially we want to restructure that data slightly, and then we have some weights, how we want to weigh these different factors, and we want to compute a dot product. Okay? So here's how we can do that, right? We can combine essentially a group by operation in green with a linear algebra operation, a dot product shown in orange here. Okay? And since this is all in the same language of formalism, we can do compiler optimizations that span these different workloads. Good. Let's look at one more example, right? So, sometimes our input data is also just text, right? So we don't even have something structured, so we need to extract the structure first, okay? So we can do some simple parsing, right? So split things by, these vertical bars, and then split things by commas, and then, maybe we want to sum each individual, the numbers in all these chunks, and compute the maximum of those, okay? So this was one advent of code challenge a couple years ago. So again, we can implement this using split operations and then traversals and group bys. But if you look at that, this doesn't look so nice, okay? And that is because the logic is kind of inverted, right? So if we specify the output object, right, then we're doing things from backwards somehow, okay? So it would be nicer to actually follow the sequence of steps, right? Say, okay, take the input, first split it by bars, then split it by commas, and then convert things to numbers, and then do the sum, and then do the maximum, okay? But again, this is also something we can easily layer on top of the intermediate language we have. We just need to provide some textual front end that has this, pipe syntax, okay? So we've built this thing as a kind of alternative entry point, and now we can write the query like this, right? So we can say we want to take the input and pipe it into the split operation. Then we want to iterate over each chunk. Then we want to split it again, iterate over it once more, convert things to numbers, build the sum, group things by the chunk, index again, and then compute the maximum. Okay? So instead of specifying how the output should look like, here we're specifying the steps that are to be taken to convert the input to the output. Okay? And the internal representation is just the same as what we've seen on the previous slide. And how does this group by operator work? It's really just constructing an object that's indexed by the relevant keys here. Good. What else can we do with this, right? So oftentimes we, don't just want to transform data, but we want to present it in some way, okay? We want to show a table or a diagram or something like that. And, since we can easily generate various forms of trees, we can generate DOM trees or React trees that will, directly, can directly map to a web page, basically, okay? So we have some simple facilities here where, we can, include a display key in our result and say, well, I want this object to be displayed as a table, okay? And then I provide the data for that. And, basically for each field, I can also say, well, this particular field, I want that to be presented not just as text, but as a bar graph, okay? So then, if I say, well, I want to have the population presented as bars here, then I get this kind of table here at the right. Now the question is, of course, well, what if my data isn't actually tabular, right? If I have like truly nested components. And the nice thing is here, we can take the nesting structure into account to build pivot tables of various forms, okay? And one of the things we can easily do with Rhyme, since the current version is embedded in JavaScript, we can use JavaScript as a meta language to compose query fragments, okay? like in LinkQ or other systems as well. So here we specify this function compute entry, which basically shows one row of the table. And we say, so this is a warehouse data set, right? We have, quantity of items available and then, models and products and so on. So we can say I want to show the quantity, I want to show the quantity as a percentage of the total, and I want to have the same thing presented as a bar graph, okay? And then I unroll this multiple levels and say, okay, first I want to group by the model, and then the product, and then the warehouse, okay? And the result, and again, sort of these things have different meaning depending on the context, right? Different levels of grouping. And if I do that, I get this kind of pivot table here, right? So you can see that we have, partial, summation, right? So subtotals, we have the grand total, which is, 100%, and then we have subtotals for each of the categories, right? So for every warehouse, we have a subtotal, San Jose, San Francisco, and then for each of the products and models, we have both the absolute numbers and percentages, okay? And of course, you can see that there's a pattern here, right? So we're unrolling things in a kind of structural way. And again, if we're composing this in JavaScript, we can make use of JavaScript itself as a macro system to implement higher level operations, right? So rather than, spelling out all this nesting, we can implement a function rollup that, just takes an array of keys by which I want to group successively, okay? And then I get the same result in just, 3 lines instead of 20. I still have to provide this compute entry function, which says, okay, for one element in the final table, what should this look like, right? Should it have a bar graph? Should it have something else? And so on. And these things are compositional, right? So I can, include, spark lines or, small embedded graphs like you can do in systems like Tableau and so on and so on. Good. We can also go even lower level, right? Do declarative visualizations directly by generating SVG trees. And, we don't have a fancy charting package or anything here, right? But we can really just say, okay, let's generate a line or a set of points or a set of bars computed from a data set, okay? And here's actually something interesting in how these things compose. So if I take this specification of our, point graph here, what this does is it takes the x and the y value of each individual point and produces one element for each point, okay? Likewise for the bars. So there's, 5 distinct bars computed, one for each point in the data set. However, this line here, that's just one SVG element, okay? And we're doing this using this string join operation here, where we take the x and y coordinates, and basically the iteration is reified at that point, right? So there's only one line generated for all the points in the data set. The nice thing, however, with these implicit iterations is that when we want to use these different charts together, we don't care if there's just one point or multiple points or a single line or multiple. We can refer to them in a uniform way, okay? So I can put all these graphs together in one diagram and overlay them, that's the first one here, by just saying, okay, I have one SVG graph and the children are, well, what I specified as bars, line, and points. Okay, so no distinction here whether it's one or multiple and so on. Okay, so basically semantically every expression returns a stream of values, and we don't need to distinguish here. Okay, likewise we can put these things side by side, essentially just by specifying an array of containers, right, and then saying each one has just one child, which is the respective diagram here. Okay. And if you want to go more fancy, you can do that as well, right? So basically every property in an SVG drawing we can, compute based on data, right? So here we just have as input a set of numbers, which we take as degrees of rotation. And, we can compute interesting things here by, just saying, okay, I want to, build one leaf here of this flower based on each value, and also change the color based on that. Okay? Good. So again, here's the end-to-end workflow, right? So the kind of way we envision this to be used is either standalone as a kind of script, but sort of the most powerful way really is in a meta-programming scenario, right? Where queries are embedded in a larger, say, JavaScript or Python program, right? So here, essentially, we have a JavaScript object constructor, right? And as we can see, this object constructor represents a RIME query, but it's itself just a JSON object in JavaScript, okay? So we can manipulate it using JavaScript, we can compose it, we can traverse it, and so on. And we have a parser that takes all the values in this object and parses them as RIME expressions. So we can have compound operations on the right-hand side here, right? We can say, okay, sum of some query operation. We also have different kinds of syntax here, right? We already talked about the pipe syntax. And we can use the meta language for composition, right? So we can pull things out and say, I have a subquery here, and then maybe using quasi-quotation, right? We're splicing that in multiple places, okay? So we don't have to repeat things. We can, factor things, abstract things, and so on. And of course, we can also, build APIs in JavaScript if the language isn't enough to add higher level abstractions. Good. From there we construct an AST that gets converted in some imperative IR, and from that we have a path that identifies the looping structure, and then we generate JavaScript and load it using eval. Okay, so obviously a future work could use WebAssembly here to make things much more efficient. Just to show what the code generation looks like, right? So on the left we have, again, a simple query that does some, relative sum here. So we can't do this in a single traversal, right? We have to do two traversals. We first have to compute the total, and then we have to compute the relative values, and that's what we see on the right here, okay? So things are factored out in such a way that the inner loop is hoisted to the top level. There we compute the total, and then we have the second loop where we're using a temporary object in a mutable way to fill in the sums and the relative sums. Okay. In the middle we have our IR, and you can see it's basically a dependency graph, and we have dependencies, and from that we determine order of statements and nesting of loops. Some very quick performance numbers, right? So this is synthetic data sets and very simple queries. But just in terms of ballpark, what we have is much more efficient than other systems. Of course, this is all with caveats, right? So Rumble, for example, is a system that's based on top of Spark. So we have the entire Spark stack contributing to overhead, which we don't have. But this is just to show that our initial compilation strategy works pretty efficiently. Good. Obviously, this is all work in progress, right? So one of the things we're currently looking at is, can we make it incremental? And there we can already see from the shape of code we generate, right? We're generating some, basically top-level loops. And it wouldn't be too hard to turn this into an incremental trigger, right? Where basically you provide, new values in a streaming fashion, and then you recompute your queries for each new data object. Okay. That's the end of my talk, right? So again, this is, very recent work, right? So still a lot of things is in development. We have things on GitHub, but I'm pretty excited about this. And some of the things we're planning to do here is add recursion, right? So that we can do, generic tree traversals, and we have some other work on Datalog engines. So that's also an obvious extension here. Then already mentioned incrementality. And of course, I think there's interesting work for compiler developers just in terms of transformations and loop analysis and so on. That's it. Thank you, and I'm happy to take questions.
Yes, we'll ask the question in the microphone. If you're watching remotely, there's a thread on Discord, and you can ask your question there. I'll be monitoring. Starting with Will.
Thanks for the talk. I'm Will. I have a question about, have you thought about how to systematically evaluate the expressiveness of this API, especially versus something like JQ? Because I assume that the kind of named logic variables for aggregation seems like the really key differentiator, but I don't have an intuition besides individual programs you could say, well, this is easy and this is hard or impossible. Like, any ideas on how to do that more systematically?
Yeah, very, very, very good question. So maybe I should point out, so maximum expressiveness really isn't our goal here, right? So at some level, we want to avoid Turing completeness, right? We want to sort of rather stay in a fragment such as Datalog, where we know that things terminate and where we know that we can generate efficient code, right? So if we have to deal with a fully general purpose language, then you know, there are always dark corners where we know we can't do much, right? So for example, I don't think we would really want to add general recursion, just because you know, if it turns into a general purpose language, then you know, we can do much less in terms of efficient compilation. That said, I think of course, you know, you want to be maximum expressiveness within the constraints, right? And there I think yeah, there's an interesting sort of spectrum, and it's not entirely clear what's the sweet spot where you want to be, right? Which things do you want to do, and which other things do you want to say, okay, look, this is not the query language for that kind of job.
Okay, thanks.
Thank you.
Thank you for the very interesting talk. I was wondering, how do you manage, how do you deal with errors, runtime error, typing errors? That is, are they encoded as an empty record, let's say?
Yeah, very good question. Errors. So this is one of the things where we're still, you know, going back and forth on some of the designs. I think what we have right now, and which is likely to stay, is that we basically treat any undefined value as an error, right? And if you think about this in a, you know, logic programming way, that makes sense to encode, you know, failures in that way, basically, right? To say, okay, if I don't produce a result, then the query doesn't, you know, there's no query result, right? It's an empty result and so on, right? Of course, the thing is you need some reification operators where you can observe failures and then, you know, act on that to provide default values and so on.
But in this case, can you, let's say, iterate on an error and obtain a result, or no?
So, I mean, the thing is also we're operating in a kind of JS ecosystem, right? So there might be an operation that throws an exception, and then we just get an exception when you try to run the query, right? So in that sense, errors are propagated.
Have you been thinking about questions of type checking, for example, knowing something about the structure of the input, inferring the structure of the output, and maybe even integration with the JSON schema as far as this is concerned?
Yes, very good question. You know, of course, we've thought about it, but I think it's too early to actually have any answers here. Of course, eventually we want to go there, and I think looking at JSON schema, that's one thing that's definitely on our agenda. Yes, thank you.
Any other question? There's none online. Anybody? Okay, so I can ask mine. So something that I'm puzzled with is how these logic variables are bound. In most of the examples, they're driven by the key, the iteration on the key, but on the tensor example, the tensor notation example, was the other way around. The keys were computed from the inner thing, and I was wondering, like, if is there a symbolic semantics that would help me make sense of that? Or
yeah, another very good question. So I think the short answer is that the scoping of logic variables is not related to the keys, because you can use the same logic variable to define keys in multiple locations, even nested locations. So in the examples here, essentially the scope of all the logic variables is global. And we have a special operator to say, okay, I want to introduce a fresh logic variable in this specific expression here. So you have to be, basically you have to manually define the scope if it should not be global.
okay. Well, let's thank the speaker again.
Thank you.